Come back to these lectures on linear algebra. Remember in the last lecture we were discussing system of linear equations. I will quickly recall what we have discussed last time. First of all, the linear equation we will denote a1 x1 plus a n xn equal to some b1, where these coefficients a1 to an are element in the field K and not all of them 0. So, at least one coefficient is non-zero and B1 is also in K, and we are looking for solution set. So, that is we are looking for all the tuples x1 to xn in k power n such that this equation holds. And we want to find a solution space, how big is it and so on, and more importantly the structure on the set of solutions. Okay, I want to improve the notation little bit so that it gives us a more possibility to generalize also. So, instead of writing in the equation form, I will just identify this with a n plus 1 tuple. So, for us a linear equation we are denoting by a tuple a1 to n comma b1, and we call it, say for example, G, and this space solution that we are going to denote LG. When also we want to insist on the field, that also we will write here LK. So, that will just to show that all these coefficients are in the field K, because sometimes it will be necessary to compare solutions with the bigger field and a smaller field, etc., etc. So, a general system of equation, finitely many equations, I will denote therefore E, and the equations are GI, I in I is a finite set. So, each GI looks like AI1, AIN, comma BI. This is ith equation. So, if you want to write an equation, you should write like this: AI1 x1 plus AIN xn equal to BI, and I varies in I. Actually, I will not deal with arbitrary case, but sometime later when I have enough opportunity, I will also tell you there is no necessary to consider only finite set of linear equations. We can deal with as many as one wants. So, it is clear that the solution space of the system E is nothing but the intersection of the solution space of all the GIs. This is clear because this means all the equations are satisfied. These are the tuples where all the equations are satisfied simultaneously. So, that is intersection. Next is when we write E0, that is instead of the equation AI1 AI n comma bi, instead of this we will replace this equation by just put bi equal to 0, AI1 AIN comma 0. So, this is called a homogeneous system corresponding to E, and we want to relate these two solution sets LKE and LKE0. First thing we have noted, that is LKE0, which is a subset of k power n, is a k subspace. So, it has a nice structure. That means, if we have two solutions of the homogeneous system, then their sum is also solutions and their scalar multiple is also a solution. This is we have checked last time. And secondly, somehow if you know one solution, if x prime, if y is y1 to yn in k power n is a special solution, I just call it special solution because we have no formal method to find a solution, but somehow if you find a solution and then call it a special solution, then we know all. Then LKE0 is translation of this solution space of the homogeneous system plus y. This means to all these solutions of E0 add y to that. So, these are all x plus y, where x is varying in the solution space of E0. This is again very easy to check. You just plug in these in the equation and you check that what about? Okay. Okay.
You can ask him.
Sorry, what do you want to do?
Nothing. So that just mistake, LKE0 instead of LKE0, it's LKE.
Yeah. Sorry. Yeah, this is LKE.
Yes. You can start fresh.
LKE is a translate of LKE0, and LKE0 plus y is, by definition, it is all the vectors in LKE0, add y to all of them. So, that is the solution space. So, this structure is this structure will allow us to draw pictures in the plane, but these drawing pictures I will postpone till I introduce a concept of affine spaces. Okay, now I want to illustrate this method by one concrete example, and which is also known as Gauss elimination. So, let us write it as example, which is Gauss elimination. This is a method to find a solution space. This is due to Gauss, therefore it is named after Gauss. I also want to introduce a language here which says that we will call E. So, we will call, I will write it here, E is called consistent, or E is said to be consistent if L of E is non-empty. That means all the equations have at least one common solution, then we will call the system to be consistent. Okay, so this process of elimination will tell both the things together, namely it will also decide whether the system is consistent or not, and in that case we will write down all the solutions by a method which is known as Gauss elimination. It is like eliminating the variables. Okay, so note that we are going to perform the elementary operations on the system E. What does that mean? That means, so there will be three kinds of elementary operations we will perform. First one of them is adding a multiple means scalar multiple of an equation in E into other equation. So this means typically I will multiply jth equation, that is we are writing it Gj, that we multiply by a scalar A and add it to the ith equation. So the ith equation will now become Gi plus Agj, and I is not I is different from J. That is, here I have written other. So first of all, note that if I do this operation and if I call the original system to be E and the new resulting system to be E prime, the solution space will not change. This is because we know the solutions, some tuple is in the solution space of E, then both Gj and Gi vanish there, and the new equation now only the ith equation is changed, namely it is replaced by Gi is replaced by Gi plus Agj. So both are 0, then the new equation also will be 0 and the remaining equations are same. So therefore in this process the solution space have not changed. So we are going to do this operation many times. This is one of them. Second one, multiplying an equation in E by a non-zero scalar multiple. So again, if the original system was E and the new system is become E double prime, then in this the ith equation Gi, if you have replaced by A times Gi, where A is non-zero, then the solution spaces are not changing again. Note this, this is very important to note, because we are working in a field and therefore non-zero, if I take a solution of E, Gi's are 0 there. If I plug in this equation, then Gix is 0, but A is non-zero, so Gi is 0. So this means the solution space is not changing. Third one, interchanging the equations. This is the easiest of all, because if you interchange the equation, if you interchange the order of the equation, then the solution space of the system does not change. So, we are going to apply these elementary operations and convert the given system of linear equations into a nice one, where we can, after looking at the new system, we should be able to detect the solutions. Okay. So, this process is well known. This is the process I am going to explain below is called Gauss elimination. So, at least one of the equation, you have a bunch of equation, and at least one of the equation, the coefficient of x1 will appear to be non-zero, because if it does not appear, then we do not need x1 in the system. That means we reduce the number of variables. So, at least we will assume, or if at least in one of the equation in E coefficient of x1 is non-zero. So, let me write down the equations in E, that is a11 x1 plus a12 x2 plus a1n x1 xn equal to b1. Second, a21 x1 a22 x2 plus a2n xn equal to b2, so on. The mth equation is am1 x1 plus a22 x2 a2n am2 plus amn xn equal to bm. So, at least one of these coefficient is non-zero. If all are 0, then we do not need x1, then we go to x2 and so on. So, even if it is in between, I am going to interchange the equation and bring it on the top position. So, we then assume a11 is non-zero. Once it is a non-zero element in the field, I will multiply this equation. I will use the first equation to kill all these coefficients. I will make this 0, this 0. That is simply because I will multiply the first equation by, for example, if I want to make this as 0, I will multiply the first equation by a11 inverse times a21 and subtract it from the second equation. I replace second equation by adding this multiple to the second equation. And similarly, I will multiply a11 inverse a31, the third equation, the first equation I will multiply by this and subtract it from the third equation, and so on. So, when I do this, so all these coefficients will become 0 other than a11. So, the new resulting system will have equations. I will just write the coefficients only. So, a11 here x1 plus a1 to x2 etc 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 a1 n xn equal to b1, and the second equation now would have changed, but I still call it the coefficients will change, but I will still the new coefficients also I will call it by aij's. So this will become a2 2 x2 plus a2 n xn equal to b2 and a2 3 x2 plus a, no, this is not 2 3, this is a 3 2 a 3 n xn equal to b3 and so on. A m2 x2 plus a m n xn equal to bm. This will be our new system now, and this is equivalent to the first one. Equivalent means they have the same solution space. Now I perform the same I do the same thing. I don't do anything with the equation 1 and look at the remaining system. It is a system in x2 to xn, and I again repeat this. Repeat means choose, I will renaming, I will assume that this coefficient is non-zero. If this is 0, I go to the next one and so on, and I perform this. So after finitely many steps I am going to arrive at the system which is like this: a11 x1 plus a12 x2 plus a1 n xn equal to b1, and again I will interchange the equations or the rename the variable. Then I will get a22 x2 plus a2 n xn equal to b2. It will go on for some time. A r r xr plus a r n xn equal to br, and then I don't have any more non-zero coefficient to choose with. So below that this side will be 0, and of course these b's are also changing. So the moment I find a non-zero on the right side, then it is immediate conclusion is this system is not consistent. That means it has no solution. So we have to get thing like this. So the remaining, these are the only r equations, and the remaining equation n minus r equations are 0. All the coefficients are 0. But then that means in the solutions, if solutions are tuples, so from first r coordinates 1 to r and r plus 1 to n, these coordinates I can take arbitrary, r plus 1 onwards I can take arbitrary coordinates, because when I plug them their coefficients are 0 here. So it's trivial that any tuple will be solution, provided I can compute the first r coordinates, and first r coordinates are computed by successively by these equations. So first start with the last equation, that is rth equation. From here I will write down what is xr. xr is, because this arr is non-zero, xr is arr inverse times a minus, because I shifted to the other side. This minus a1 minus already taken out. So a11 x1, no, not a11, the second term here, that is r plus 1 xr and so on, go until ar n xn. This and this BR as it is plus BR. BR, this is X. No, this is correct because this one. Oh, this one. Yeah, sorry. I should take a bigger. This is X R plus 1 and so on. So now I got XR from this equation. Earlier equation, I will take XR minus 1 and plug in this XR there. So that way I get the solutions. So let me do one numerical example to do this process. Understandable. So suppose I take 3 equations in 4 variables. So I have written down the coefficients here. 2x1 plus x2 minus 2x3 plus 3x4 equal to 1. Second equation is 3x1 plus 2x2 minus x3 plus 2x4 equal to 4. 3x1 plus 3x2 plus 3x3 minus 3x4 equal to 6. The field we are working is the field of rational numbers. So obviously this element itself is non-zero, so I will use that. I will take this element which is non-zero and use this to kill these equations. So that means I am going to replace, to killing this I have to multiply this equation by half and multiply by 3. So multiply this first equation by, so I will write here minus 3 by 2, the first equation, add it to the second one. So G2 we will replace by this new equation. G3 we will replace by same minus 3 by 2 G1 plus G2 G3. So I will just write the coefficient. So and also I could multiply the first equation by half. The first equation G1 replaced by half G1 to make the coefficient 1 there. So the first equation will become x1 plus half minus half x2 minus x3 plus 3 by 2 x4, that is the first equation equal to half. The second one, the first coefficient, the coefficient of x1 is killed by our choice, and the second one will become we are multiplying this by minus 3 by 2 and adding it here. So half will remain, half x2 plus here it will remain 2x3 because we are multiplying this by 3 minus 3 by 2, so this will become 3 plus adding it here it will become 2x3 plus here it should become minus 3 by 2 we are multiplying, so minus 9 by 2 and we are adding it here, so it will become minus 5 by 2 x4 and this will become 5 by 2 because this is minus 3 by 2 added to 4 is become 5 by 2 plus. The second one similarly will be 3 by 2 x2 plus 6 x3 minus 15 by 2 x4 equal to, okay, let me do this just for I want to do multiple examples in the same. So I want to not take 6 here, but I want to take a constant b, where b is some constant. And the problem I want to find is for which b it has a solution. So this will become b minus 3 by 2. Now I can again, for the simplicity of calculation, I will multiply the second equation by half by 2, so that the fraction will not be there. So multiply this by 2. So I will correct here. So this will become 1, this will become 4, and this will become minus 5, and this will become 5. And now I will use to kill this. So that means I have to multiply this by 3 by 2 minus 3 by 2 and add it here. So this will go, and what will happen here, minus 3 by 2, so that is what will be there? Oh, this will go, this will be 0, and this one here 12 by 4, that is minus 6, and this will also become 0, and this is plus 15 by 2, this is minus 15 by 2, so this is 0, and this will become what? This will become, there was 5 here, 5 into minus 3 by 2, and we are adding it here, so this will become plus 15 by 2, which is b minus or plus, did I make a mistake?
Plus.
No, this is minus, because this is minus. So this is minus, this is minus. So this will become minus 18 by 2, that is 9, b minus 9. So the third equation became 0 equal to b minus 9. So if this system has to be consistent, then we should get 0 equal to 0. So it has, the solution exists if and only if b equal to 9. And in that case, now we have to forget the third equation, and the first two equations from the second one, you write down x2 in terms of x3, x4, and then use this result and the equation 1 to write down x1. So that one we will get all the 4 coordinates. The third and fourth coordinate are arbitrary, and first two coordinates are determined by the first two equations. I think we will stop for a break and continue later.